Hello everyone, my name is Andrew Berguch and I am from the University of Waterloo, which is just outside Toronto in Canada. It is with great pleasure that I am presenting this talk today in the very first virtual conference on structural integrity. The focus of my talk will be on the multi-axial cyclic behavior and fatigue modeling of forged AZ80 magnesium alloy. I'd like to acknowledge the support of the funding agencies and industrial partners who made this work possible, shown below. This particular presentation is detailing the nuances of multi-axial behavior and fatigue of magnesium alloys, but is part of a larger project where we actually designed, analyzed, and optimized, as well as manufactured automotive suspension components for magnesium for vehicle lightweighting initiatives. Some background and motivation for the work. As many of you may know, within the transportation industry, corporate average fuel economy or CAFE requirements stipulate ever-increasing fuel efficiency and reduced emissions year after year. One of the most effective ways of achieving this is a new emerging philosophy called multi-material lightweight vehicles, or MMLVs. This concept deals with not only substituting a conventional material for a lightweight one, but the lightweight material must be used in a location where its performance is optimal. For example, a B-pillar where strength and stiffness are important, steel might be the optimum material. However, in frontal or rearward crash where the vehicle's crumple zones are engaged, aluminum performs well. It has good ductility and energy absorption. For components which are driven by cyclic loading or fatigue, such as a suspension control arm illustrated here, there is a unique opportunity to utilize magnesium. It offers superior performance to all other structural metals in this environment. Magnesium offers similar strength and fatigue properties to aluminum, however at 2/3 of the mass. The weight savings versus steel is even more pronounced at over 77%. So exploiting the benefits of the space-age material to their full potential would have a profound impact for an entire vehicle. This Ford Fusion that we've investigated here, a weight savings of over 70 kilograms is attainable. Seen on the right is an elastoplastic simulation of the critical service load cases for the component which we intended to forge, which is a front suspension component on a passenger vehicle. You clearly can see that the deformation is highly three-dimensional and the resulting stress state is highly multi-axial, which is why we're interested in the multi-axial behavior of magnesium in the first place. So one might ask themselves, if the properties of forged magnesium are arguably superior, why hasn't this material been utilized for such components already? The answer to this question has many facets, one of which is the poor formability of magnesium at room temperature. This figure shows the critical resolve shear stress versus temperature for a variety of different deformation modes. At room temperature, basal slip is the first one that becomes active in the lowest critical resolve shear stress range of 2 to 4 megapascal. If the grain orientation is not favorable to activate basal slip, then extension twinning will be active here in the range of 7 to 10 megapascals, followed by prismatic, pyramidal, and contraction twinning. Von Mises' criterion states that for arbitrary plastic deformation, at least 5 independent slip systems need to be able to be activated. At room temperature, this is very difficult with magnesium, as basal slip is typically what is dominating. However, at elevated temperatures in the range of 225 to 425 degrees Celsius, the critical resolve shear stress of the other modes decreases dramatically, improving the ability to plastically deform and thus the formability of the material. So what this means is that to successfully process magnesium and achieve large strain via forging, it must be done at this elevated temperature regime. This introduction of temperature into the processing equation complicates controlling the resulting microstructure quite a bit, as well as the fatigue behavior, as the process is now highly thermomechanical. One of the other unique features of wrought forms of magnesium is its unusual behavior at room temperature, almost always displaying a monotonic and cyclic response, which is both asymmetric and anisotropic. Yield asymmetry shown here is a phenomenon which is very common in most wrought forms of magnesium alloy, and the cause is linked to the hexagonal closed pack structure, as you can see here. In tension, basal slip is active, indicating by this monotonic curve, a hardening behavior here. In compression, twinning is active, which is manifesting itself as the sigmoidal hardening behavior here. Anisotropy is also another well-known phenomenon which is present in most wrought forms of magnesium alloy with sharp texture. In essence, it describes the dependence of the material properties on the direction relative to the crystallographic axes. Take now, for example, these tensile dog bones that were taken from an extruded billet of magnesium in the extrusion direction here and the radial direction here. It is well known that AZ80 magnesium extrusion has its crystals oriented such that the C-axis is in the radial direction, as shown here. When deformed in tension, a sample taken from the extrusion direction will exhibit basal slip, and monotonic hardening is indicated by this black curve on the left. However, when deformed in the radial direction, basal slip is not favorable and extension twinning happens instead. This manifests itself as a sigmoidal hardening behavior once again, and a premature yield stress. So important to note here is that the material behaves vastly different in monotonic tension depending on the direction which you are deforming it. So this anisotropic nature of magnesium will subsequently be discussed in more detail. The material utilized to produce test specimens was produced using a closed die forging technique. The initial cylindrical billet shown here was heated to various temperatures and then forged at 20 millimeters per second in heated dies which restrict the material flow in both in-plane directions. These dies have this internal I-beam cavity, which is typical for structural components which try and maximize bending stiffness to have this high inertia cross-section. The contour plot on the top right shows the evolution of strain throughout the cross-section of the forging, predicted through a finite element model. It can be observed that the billet undergoes the forging process from a circular cross-section to this I-beam profile. The details by which the experimental investigations to characterize both the structure and properties were conducted as follows. Biaxial fatigue tests were done over several frequencies ranging from 0.1 Hz to 30 Hz to maintain an approximately equivalent strain rate between all of the tests. Both the monotonic and fatigue tests were conducted using servohydraulic controlled load frames with digital image correlation used to measure the strain in the monotonic tests, and an extensometer used to measure the strain in the fatigue tests. The chemistry of the alloy was obtained via scanning electron microscopy with EDS for chemistry, the microstructure with light optical microscopy, and the texture with X-ray diffraction shown here. The fracture surfaces of the monotonic and fatigue samples were investigated using SEM as well. The superficial hardness was measured using a computer-controlled hardness tester with a Rockwell 30-ton scale. As discussed previously, one key characteristic of magnesium is it is comparatively low number of slip systems relative to other FCC or BCC metals. Due to this, there isn't a lot of options for the material to deform when subjected to a cyclic load. So this illuminates a large reason why we are interested in the biaxial fatigue of magnesium alloys in the first place, since these low number of slip systems effectively confine the plasticity to be very stress and loading orientation specific. Non-proportional loading, which effectively rotates the principal axes, can cause irreversible plastic deformation and damage on planes which were otherwise unaffected or inaccessible by the limited number of deformation mechanisms that MG has available that I previously discussed. Once again, similar to many others doing work in multi-axial fatigue, we utilized a thin wall tubular specimen illustrated in the top left here, and 5 different loading paths, pure axial shown here, pure shear shown here, as well as a proportional axial and shear loading path here, as well as 2 non-proportional paths with a phase angle of 45 degrees shown here and 90 degrees shown here. The discussion regarding the crystal structure of magnesium and resulting asymmetry and anisotropy has hopefully highlighted to the audience that the cyclic behavior of magnesium alloys are highly dependent on the loading history, such that when the material is forged, the crystal structure reorients itself to have the C-axis aligned with the local forging direction of the material. Following warm forging, the microstructure is effectively frozen, preserving the texture. However, the warm temperature and slow cooling rate are enough to annihilate any of the residual twins which remain, meaning that the microstructure that's observed of the forged material is virtually free of twins and has a local texture that varies throughout the cross-section of the forging, as illustrated here. Now looking at the uniaxial fatigue results for a variety of different forging conditions, the base extruded material condition is illustrated here, as well as the forged material condition illustrated by the red lines. It is well known that for wrought magnesium alloys, typically they display this asymmetric cyclic response, as can be observed by the hysteresis loops illustrated here and here. This is due to the twinning in the compressive reversal, so this downward reversal, which causes a lower peak stress observed in compression. This is followed by detwinning in the first part of the tensile or upward reversal, which is then exhausted and followed by hard pyramidal slip, and this results in a higher peak stress that's observed in tension. The question is now, how does this asymmetric response affect the biaxial response of the material in fatigue? Now looking at the stabilized pure axial and pure shear cyclic response for a fully reversed axial strain amplitude of 1% on the left and 1% shear on the right, it can be observed that, similar to the previous slide, there is an apparent asymmetry of the axial response, whereas in shear it is virtually symmetric. Now adding the biaxial proportional loading, which are these dashed lines, it can be observed that the axial response is virtually identical, whereas the presence of the axial strain has dramatically lowered the shear stresses in both directions, the peaks, as shown in the figure on the right here. Now, if we look at non-proportional loading at 45 degrees, it can also be observed that the axial response is still virtually identical to the previous cases, being the uniaxial and proportional biaxial. Now, the shear strain in this case was controlled to be at a lower strain level of 0.5%, as seen in the figure right here. The reason for this is that this particular loading history is representative of the service loads for the actual component that we discussed in the motivation part of this presentation. Despite this, you can still observe that the shear response remains symmetric, and the peak and valley of this hysteresis loop has become very blunted due to the presence of this axial response on the left. The modification to the cyclic behavior is a direct result of the presence of the axial loading dominating the cyclic behavior, and this is an important concept that will form the basis for the modeling of the fatigue behavior, which I will discuss in a few slides. Finally, when we increase this non-proportionality to be out of phase by 90 degrees, we can observe that once again, the axial response remains virtually identical to all of the previous cases, whereas the shear response once again has been affected by the increase in this non-proportionality. Important to note is that the plastic strain energy density for the shear response, which is signified by the area enveloped in these hysteresis loops, has decreased with increasing phase angle, and this is an important observation which I will discuss later. Now, to summarize the strain life curves for each of these cases, this slide illustrates the pure axial behavior. So this is strain amplitude on the y-axis versus number of cycles to failure on the x. Here is the pure shear behavior with the von Mises equivalent strain amplitude being graphed on the y-axis as shown. It can be observed that in the high cycle regime, the behavior between pure axial and pure shear is virtually identical. Now, adding the proportional biaxial cases, it can be seen that they behave somewhat as one would expect, as an average of the axial and the shear responses, so it's somewhat in between these two curves here. Since there is no rotation of the principal axis here, the damage is accumulating along the same planes that were accessible of each of the uniaxial cases. However, what's quite interesting is when we look at the non-proportional data, a dramatic shift in the behavior can be observed, such that for a given strain amplitude, a lower number of lives is observed. So as that can be seen by these blue data points as shown here. This is typical of ductile materials that observe a degradation in fatigue life as a result of non-proportionality effect. And this material is ductile as it has a 20% failure elongation, so this is fairly typical in line with what other researchers would find. The damage is now accumulating along different planes, resulting from the rotation of the principal axis, and this results in a detrimental effect on fatigue. This effect is now even more exaggerated in the 90-degree out-of-phase case, where the increase in non-proportionality further decreases the fatigue performance. Now, there are a large number of damage parameters available for modeling fatigue. Of those, a smaller subset exists which work well for materials with asymmetric and anisotropic behavior. Using energy as the basis for a damage parameter is a robust method for magnesium alloys, since it's a scalar quantity that is invariant of direction, so it's quite convenient too. The quantities that are required for the model are the plastic strain energy density, which is signified by this yellow area enveloped in the hysteresis loop here, and then the elastic strain energy density, which is this gray triangular area here. The model takes into the form of a Coffin-Manson relationship, however, instead uses strain energy density versus number of reversals to generate the calibration constants that are required. The model is a quite simple model in the fact that the life prediction is just a weighted average of the axial and shear fatigue life predictions that were calibrated from the energy life curves for each of the uniaxial cases. This individual weighting factor of 0.3 here places more emphasis on the axial energies being more damaging, as it's kind of artificially penalizing the shear direction, since it dominates, the axial direction dominates the biaxial response, as well as the crack orientation, which I'll discuss in the subsequent slide. You can see in the image on the right here the total strain energy density versus number of cycles for all of the 5 loading paths that were observed here. Now looking at the fatigue life prediction for all of the 5 loading paths, it can be observed that virtually all of the fatigue life predictions are within a band of plus or minus 2, which can be considered to be a very good and reliable prediction. The non-proportional cases are trending towards non-conservative, which is a focus of future work in refining this damage model. Now finally looking at the macroscopic crack orientation, it can be observed that in the pure shear case, the crack initiates on the surface of the sample and then progresses longitudinally along the sample axes. However, for all of the biaxial cases, the cracks still nucleate at the surface. However, they progress in a mode 1 opening mode, which is perpendicular to the loading direction illustrated here, here, and here. This supports the previous observation that the axial response and damage is governing the fatigue behavior. In conclusion, near net shape closed eye warm forging of extruded AZ80 magnesium results in a structure that yields both good strength and ductility for automotive suspension applications. Some concluding remarks are, due to the limited number of slip systems available at room temperature, the cyclic response of magnesium is quite complex, as illustrated in the presentation. The rotation of the principal axis in non-proportional loading causes damage to accumulate along different planes and a lower life, which is typical of a ductile material. Strain energy density is a good damage parameter for magnesium because it's a scalar quantity that is invariant of the material direction. So this is something that was demonstrated to be quite robust and convenient with asymmetric and anisotropic materials such as the forged magnesium that we have investigated here. Finally, the crack orientation in biaxial loading is dominated by a mode 1 crack that is perpendicular to the loading axis and does not resemble the crack observed in the pure shear case. Thank you for your attention. I look forward to any questions from the audience in the online discussion. In closing, I'd like to challenge the audience to tell me a concern that they may have as researchers towards using magnesium as a material for fatigue critical applications. Thank you.